I'm Stewart. I am the OPAL architect at IBM, which basically means I do a whole lot of firmware things. And today I'm talking about what happens when you plug in a system up to the point where you get a login prompt that you care about. So this is going from box sitting on a desk, power cord goes in, how do you get to then being a computer that you want to use? And I'm going to talk about a system that's roughly similar to our IBM Witherspoon model, or I believe the commercial name is IBM AC922, which is a name that apparently you sell the machine as, but not that everyone knows it when you're doing the years of bring up beforehand. It's a Power 9 system. It's one of the first Power 9 systems to ship. It's part of the Coral Labs supercomputers, like at Lawrence Livermore and Oak Ridge. So number 1 and 3 on the top 500 supercomputers. That's this. It's based on Power 9, which looks like that. But our story doesn't start with Power 9. The system we're talking about here is similar to like the Talos systems as well. Functionally equivalent, different price points, similar architecture. It starts with the BMC. So this is a service processor. And one of its jobs is to turn on the main processor. So you have a service processor out to the side that does out-of-band management. So it does things like allow you to use IPMI to power on the computer, to get a serial console, to power off the computer, to see what's the status of fans. And it's a pretty much standard ARM environment. If you're at all familiar with sort of embedded ARM Linux systems, or as I like to call whatever random computing device I get at home, yet another embedded ARM Linux device that's going to sit on a shelf for a little while and then migrate to my garage and be found 5 years later and go, oh look, it's yet another ARM embedded Linux device. So we have a computer inside your computer. It's got U-boot, it's got Linux on NOR Flash, usually using something like JFFS2 or UBIFS. It has user space stack running on top of a standard Linux kernel. And there's various configurations that will happen on different systems. So like on the Witherspoon system has some configurations options set that's different than like a Talos system. And something like what do we call Boston that we release it? Anyway, the other systems we have may have a different BMC stack, but it's still essentially an embedded ARM Linux computer. And what is the other thing that these things operate? The power button. So like if you're using this more as a desktop, like more of a Talos machine than a server, like a Witherspoon, once it is up, it can look for the GPIO, the physical power button, because it turns out that some people want a physical power button on their computers. I don't know why don't you all just remote manage all your servers? Why would you walk up to one and press a physical power button? There's a remote one. You don't have to get up. You can sit at your desk and press the power button. Like, why would you have to go to a data center? It can also be a virtual power button, right? So it could be over IPMI or Redfish or any kind of interface. And what does the power button do? Well, it has to kick off booting the main computer, the Power 9. But what does the BMC booting look like? Luckily, we have a simulation environment that is nicely documented. And it looks exactly like an embedded ARM computer. If you've ever used any kind of thing that looks like ARM and Linux, it looks like this, right? U-boot, loads of kernel, loads of RAM disk, boots. No. So this is what you get on the serial port that's directly to the BMC. So there's usually a header on the board that has a UART that's a BMC serial port, and then you can see the BMC boot. Yeah, this is physically next to the machine, but this is what's happening before the power button works. So like on a Talos system, when it's flashing a light, getting ready, after you plug in the power cord, it's doing this, and the same on like a Witherspoon. On the minute or two after you plug in the power cord, as in roughly about this long, from when you plug in the power cord to when you can press the power button and power on the system, it's booting.
So it's useless to do anything on the power button while it's flashing.
Yeah. I think it's physically flashing. I mostly use them remotely, so I'm not sure on the physical lights. I'm pretty sure we need some webcams in some data centers looking at lights and some image recognition to test this, because all of us use the machines over in the other room and don't look at them.
Don't forget that sometimes when you have an issue, you are next to the machine in the lab and you have no control.
Yep, that is true. Yeah.
You have only your fingers in this case and your eyes.
There we go. So the comment there is that the light won't flash until the BMC is running on a bunch of systems. So it depends on what system, on whether you have a physical light that flashes or not. So where is the thing there? But yeah, the BMC is now booted. So we're up to the point now, which I have in slides, which is what does the power button do? Well, runs a little piece of software on the BMC, and its job is to fliddle some bits to tell the P9 chip that it's time to boot, right? So simple little twiddle some GPIOs. And then we engage what's known as the self-boot engine. So inside the Power 9 chip, there is all of your Power 9 cores that do, your real compute. But there's another embedded processor. Actually, there are many embedded processors because not only is there a computer inside your computer, there are processors inside your processor. Because it is, in fact, turtles all of the way down, completely all the way down, and lots of computers. Yeah.
Can you make a parallel with what we see on the SOL?
Can we see on the SOL? Yep, yep. We're not up to SOL yet. So at this point, you've not gotten anything over a serial port. You've just pushed your button, and we are now starting the self-boot engine. The question of pushing the power button remotely, this could be IPMI tool power on. It could be going to the web UI and clicking power on. It could be over Redfish if it supports Redfish, or it could be over the REST API. Or it could be SSHing to the BMC and typing obmc util power on. Any of those is functionally equivalent. All you've done is told the BMC that somehow you want to twiddle the GPIOs to say, hey, go boot the SBE. And what does the SBE do? Well, its job is really simple. It's a tiny little processor, and its job is to get one core, that's a Power 9 core, up to a state where it can run instructions out of L3 cache, and to put something in that cache that it can execute to load the next bit of firmware. So there is a tiny bit of ROM, or CPROM, inside the P9 chip that contains the self-boot engine firmware. And this is the core root of trust for your system as well. So it's going to do the first bit of load of firmware, the first bit of verification. I'm going to go from there. And the job it's going to start is sort of the left-hand side here. So this is a flowchart that's in OpenPOWER GitHub organization for P9 IPL flow. And we have the very first stages of SBE boot. And we don't really need to go through the details. You can go and read the boring details or the exciting details of how your computer boots a bit later. But the initial program load, or IPL as I probably keep calling it, is probably a uniquely IBM term, and it probably dates because IBM's done computers for a very, very long time and therefore came up with it before people called it booting. So if I say IPL, it means booting, and I've just been assimilated into the IBM hive mind of terminology. And so what does this sort of tell us? Well, CPUs don't just work, right? You don't just, it's not like the good old days of the Z80 or the 6502 where you just apply some current and it starts executing instructions, right? We have a computer inside the computer that is roughly that, right? But we do actually have a lot of setup to do, right, to get things going. In the dim dark past, we didn't have a self-boot engine. What happened was the service processor would do all of its work, right? So with Power 8, we had the start of having an engine inside the chip that could boot the chip, and it's called a self-boot engine because the chip is booting itself, right? And this is how most modern processors work. The reason we didn't need one previously is that there was always a sophisticated service processor with a lot of intimate knowledge about how to boot the computer, right? And with the BMC stack on OpenPOWER systems, we decouple them, right? It needs some knowledge of the system, but it doesn't need in-depth knowledge of the inside of the chip. And that's a feature for ease of development. So what do we mean by security? There are two separate security domains in an OpenPOWER system, right? we try and have it so the BMC doesn't have to trust the host, and the host doesn't have to trust the BMC. That is, the secure boot implementation on the host processor only concentrates with itself and doesn't assume that the BMC is trusted. And so you could have separate entities going. And the SPE engine itself is the core root of trust. So it has inside that CPROM a hash of the core firmware secure boot keys. And so as it loads the next bit of firmware off flash, it verifies that those hashes match. And if it does, it continues to boot. And if it doesn't, you don't boot. If it doesn't, this is actually before we have serial over LAN console. So what you have is then a computer that says powered on and you get no printout, which isn't ideal. But if you've got to that problem, you've got bigger firmware problems. But this is the core root of trust. To make that obviously so that you can't just overwrite that at runtime, there is a flag that gets set early in boot that says you can no longer update that CPROM until you re-IPL. So you can do a firmware update of the CPROM. It happens really early in boot after there's been signature verification. And you can also, if you have the secure boot jumper set so you're not doing secure boot, you can then write it from the BMC as well to unbrick a chip. So where are we up to? Getting a call going. Basically, what happens is that we have to do a thing called scan in the scan rings, which is basically there's a giant shift register inside the chip that sets a bunch of settings, which are the magic settings that means the chip will start executing instructions with these things set, right? So you design a chip, you don't know all of the details for the physical properties of it, and you might not know whether certain functionality is going to work when you actually fab it. So you have a bunch of little switches. And so we scan that in, we do a bunch of other inits going on really early on to get the CPU core up and running. So what the SPE does is it writes all these values in and sets it up, and then it gets what we call the Hostboot bootloader from that CPROM and puts it into L3 cache. And it's a tiny bit of code whose only job is to execute in the Power9 chip and read the next stage of firmware, right? Because we don't have much room inside that SPE CPROM, so we go and load the Hostboot bootloader. And its job is to be the very first instructions that are executed on the Power9. So we still don't have anything over serial over LAN, but we are now executing instructions on the Power9 chip as opposed to the self-boot engine or the service processor. And its job here is to load the Hostboot base image, which is the very first sort of large bit of firmware. So remember, at this point, we don't have RAM. We're just in L3 cache. We don't have any other cores. We don't have any SMP. We don't have PCI. We don't have any power saving, so we're running the core clock at a pretty low value. And we don't have all those fancy things, right? We just have one little core executing some code that is more powerful than any computer we had in the 80s. But it's still like actually probably even more than 10 years ago, like crazy amount of computing power, but relatively simple and slow compared to a full, 2-socket plus Power9 system. So we're up to the Hostboot bootloader, loading the Hostboot base image. So this giant IPL foam thing there, we're at start bootloader here, and guess what we have now? The next steps, right? And so the next steps are all these various IPL steps. And what do we have to do during all of that setup? So this is when you see the banner, the first thing you will see on a serial over LAN connection, welcome to Hostboot, right? And you'll see iStep 6 dot something. Let's see if I can very quickly show this. Reboot. So this is a machine rebooting, so it's going to start reboot and take a second, but that'll show in a second. So what do we need to do inside these iSteps? Well, we have to bring up the other cores. We have to bring up DRAM. We have to inform the service processor about our machine inventory and stuff like that. We need to find what DIMMs are there. We need to set up SMP links. We need to make sure that everyone thinks the right time is the right time, for example. And so there's a whole bunch of init that goes on. We might have, different sort of peripherals we need to train. So on some systems, there might be like memory buffers or something like that. There will be a whole bunch of registers that we need to set to some default values. All sorts of little steps along the way. Here it is, welcome to Hostboot, secure and valid. So now we are out of the SPE, we are into Hostboot. So we're in the Hostboot base image, and what it does is actually has a lot of code in it. So it's not just the base image that gets loaded, it has an extended image and actually pages in pages of memory from Flash. So it's like a tiny operating system with a memory management and swap in order to get enough code running in L3 before you get up to DRAM. So when we get into DRAM init, like 13, 14, you see this, DRAM init, mem diag, we're now zeroing our memory because we have ECC memory, so we need to set all the flag stuff there. And now we're sort of exited cache contained, and now we're on to the next IPL step, which goes, of course, faster than my slides will do. So, could talk quicker than demo. But one of the stages that happens in here is we have to set up for power saving states. So what we call is we have a stop image. And part of this image is to be able to have a CPU core that we turn off, right? It's really low power saving if you turn something off, but we need to be able to turn it back on again. So we have a stop instruction, which is, hey, stop the CPU, and then we have a method to resume it. So it really should be like a resume image rather than stop, but that's how we go. We have another bit of firmware called H-code, which is the code that runs on this tiny little other embedded processor inside your processor next to the core, and its job is to turn the core back on. Its main job. So as you go into a low power state at runtime, its job is to be able to turn that core back on and restore some register state enough so that Linux can get back up and running. So the idea is if you have bursty workloads or something running at runtime, we can turn off some cores to save some power, and we can also turn off some cores to save some power so we can clock other cores at a higher frequency. So part of the job in this whole init is to set up the stop image and load the H-code firmware up and get that going. Its also job is to get the OCC running. So the OCC is the on-chip controller, which is another embedded processor inside your processor. And it's a 32-bit PowerPC system with a bunch of little helpers of PEPI engines, so more processors to help it. And it has a couple of jobs. Its main job, as we say, is CPU frequency scaling and to enforce hard power limits. So its job is basically, keep within a certain amount of power consumption, be able to scale frequency up to do bursts and sort of ultra turbo frequencies, as well as it does some things to help get some debug data out, like in the case of a check stop. The check stop is when the processor hits a condition that it can no longer continue to execute without possibly acting on bad data, so we stop the world. The logic being that we will not possibly execute instructions based on bad data. So the chip will stop itself rather than possibly acting on bad data. And there are some error conditions you can have in the chip, either due to hardware faults or software faults that basically trigger that condition. So the OCC gets set up and started. It has its own bit of firmware that's got loaded into the OCC, and then it does its boot process. And it has a little bit of shared memory that we communicate with the rest of runtime firmware, as well as boot time to be able to say, here are the CPU frequencies you can do and control it, as well as it does some sensor management and stuff like that. We also have what we refer to as Hostboot runtime, which is a bunch of runtime diagnostics and repair code. This is run through the OPAL PRD application. So this is actually a bit of firmware that we run in user space, right? So when you start the OPAL PRD application from Linux, it will do Hostboot runtime code to do specific diagnostics and repair at runtime based on that actual machine. So it's like we run it in user space because then if there's any bugs in that code, guess what? You get a seg fault, not a giant crash or scribbling over in-memory data. And it can also process error logs, do some DRAM repair and other preventive maintenance and stuff like that as well. But we also set up Hostboot runtime and Hostboot. And now we get to the next stage of firmware, which is skiboot, which is what I primarily work on. So Hostboot at this point has verified, as in done secure boot signature verification on all the previous components. And then it goes and loads skiboot, which is also verified. So we're still doing that firmware secure boot stuff. Skiboot does boot and runtime firmware as well. So it has some of the job of booting the machine, as well as the job of being the bit of firmware that stays resident at runtime. So OPAL calls is what skiboot implements, and this is what the Linux kernel uses to make firmware calls at runtime. And this means that we don't have to have intimate knowledge of each bit of hardware in Linux. We can abstract that away through OPAL. So the idea is that skiboot provides the absolute minimal layer of runtime firmware to do that job, and not anymore. Its design choice is that Linux is always in charge, So OPAL never receives interrupts by itself. It's always Linux gets it first and passes it through. And the idea is Linux is in charge. We're essentially a shared library. We're in the same address space, and it's just here's the calling convention to make function calls. That's it. Really, really simple stuff. So we init things like the chip TOD, so that's the time-based register. We use the SBE for like runtime stuff. We do a bunch of I2C, sensors, and VRAM, stop states, and frequency scaling, and mapping that to what Linux can understand. We have the NX unit we set up. We scan PCI. We set up NVLink, like CAPI and OpenCAPI. And then we load and boot a Linux kernel. So from Flash, we have we have the last step of skiboot is to load from Flash an embedded Linux kernel. So we have a Linux kernel and user space in Flash that runs a user space application called Petitboot, because we needed a menu option to select what OS you want to boot. And it turns out that we had drivers for all our I/O devices in Linux already, and it's quite nice to write a UI in user space rather than kernel space. So to save ourselves having to re-implement everything again, we just used Linux and store it in Flash. So we boot an embedded Linux system. And all this does is provide a nice user interface around kexec. So you're running a kernel, it finds what kernels you can boot and what OSs. You hit, hey, please boot it. So we do the find OS stage. You know, we discover block devices, network devices, get DHCP, and then we kexec. And our job is to make sure kexec, of course, always work. And at this point, we leave that boot environment, so we leave that embedded Linux environment, it's gone, and now we actually have your standard Linux, as in your Ubuntu, your Red Hat, or Debian, or Fedora, or your own distro. Another question? Yeah, that's how it looks like the computer's shutting down just before we boot. Yeah, we should really change that message. Yeah. But yes, that's the last bit where you have the Petitboot menu, and when it's booting that, it goes, oh, shutting down, starting things again. So at this point, we're now booting standard Linux, and this is the point where firmware job is to just be the runtime component, and we're now into your normal OS. Apparently the FreeBSD guys have got things running as well, so you could also kexec FreeBSD, which is kind of nice to see a second thing. Second OS. Where did I go? And here's one I prepared earlier. Hey, look, it's a login prompt. Yay! Very exciting. So what do we also have that can be do there as firmware? Well, we also have a feature called fast reboot, which is a way to reboot in a handful of seconds rather than a couple of minutes. And we do this by not reinitializing everything, right? We only re-unit a subset of hardware. Like, we don't retrain DRAM, and we don't, reset up the OCC or H code, but we do, rescan PCI, we reset a bunch of core state, we clear NVRAM, we clear a bunch of registers, and we reload Petitboot. So the downside of fast reboot is, of course, you don't get the same trusted boot state in the TPM, right? And there's always the chance that we have a bug and that doesn't work as well. But it does mean that you can type reboot and get your next OS up in a handful of seconds. So if you're doing a security update on an OS, it means your sort of downtime and reboot cycle is a lot less. That works on a bunch of machines, not all of them, because we don't have the code there to like re-init NVLink hardware. So for the Witherspoon system, that doesn't work, but for other systems, it does. And the other time of boot that we have, I just wanted to put in one more thing, because the team scrambling together a demo to do this, and they're like, "Here you are." We have a thing called MPIPL. So this is memory preserving IPL. The idea, and this is currently in development, the idea is when you crash the OS or certain error conditions inside the chip, what you do is, instead of doing a full reboot, which clears memory, is you do a reboot in a subset of RAM that you've reserved, re-init a whole bunch of stuff, and then copy the contents of the memory from the crashed instance into a core file, and now you have the ability to do a crash dump analysis because you get a core, but of your computer and of your firmware. So you use all the standard like kdump tools that come with Linux to trace what might have gone wrong in firmware, what might have gone wrong in the kernel. And so this is the absolute fast forward demo that's right at the end as I'm running out of time. So I will play it fast and attempt to say, here's the magic sysrq trigger to trigger a crash. It goes, hey, look, yep, we crashed. And it will now attempt to reboot, and we'll do a memory preserving IPL. So at that, I think I'm right at the end of the time as well, with 1 minute to go, and we'll see how fast this can possibly play. But this is sort of something that's coming as sort of a nearby firmware feature, which is kind of neat. And so hopefully we will get that going. It takes a bit of time to get some dumping. So this is like the status of the debug bits of firmware to make sure that it happens. But at this point, it should actually start sort of booting again in a second, and it will go back, and we'll be able to take a crash dump, and it does a little bit of analysis. But is there any sort of final questions as the magic demo of how to debug your system better than probably any other development workstation in the world could do? So in the background of this is the point where you've now got a dump file, so you've now got a core dump of your entire memory content, whether you had a kernel bug or firmware bug, and you can now use the crash tool to get back traces on what happened and cause your machine to crash. So if you're doing low-level kernel development or driver development or firmware development, this will enable you to sort of much better diagnose things in band without having to attach an external debug box. And I think I'm well out of time.